Hi, my name is Benjamin Aubin. I'm a PhD student at the Institut Physique Théorique in Paris under the supervision of Lenkas de Borova and Florent Zakala. I will introduce you to computational gaps in two-layer neural networks. In the recent years, it became of great interest to know if we can efficiently learn a teacher network from a limited number of samples. We propose a theoretical approach based on a teacher-student typical case scenario, and we consider a two-layer neural network with fixed weights in the second layer, called a committee machine in the physics literature. The teacher with weights W star is fed with IID random samples and generates output Y star. The student has the same architecture and wants to learn W star using the training set provided by the teacher. Let me emphasize we consider a theoretical infinite input size limit and the ratio between the number of samples and input size of order 1. Our goal here is to understand if this learning task is possible and to quantify the effectiveness of neural networks in this simple model. Our main result deals with the generalization error in the base optimal case. In the infinite size limit, we provide an explicit formula for the generalization error that depends only on the overlap parameter Q star. In fact, this parameter can be computed as a critical point of the replica mutual information. This mutual information was well known to physicists since the 80s, but our first contribution is to provide a rigorous proof using the adaptative Guerra interpolation. Our second contribution is the design of a polynomial time message passing algorithm, which is conjectured to be optimal in many cases. To illustrate, we consider Gaussian weights with sign activation functions and a large number of hidden units k. We compare the base optimal generalization error with a full line and the generalization performed by the IMP algorithm with dots. For a small number of samples, the IMP algorithm follows the optimal generalization error. They both decrease and then plateau. In this regime, the optimal solution has non-specialized hidden units, meaning that the student believes in linearly separable data. We then observe a discontinuous specialization transition at which the optimal generalization error jumps and then decreases to zero. In this regime, the student is theoretically able to find a solution with specialized hidden units, meaning he understands that data are in fact non-linearly separable. However, the IMP algorithm does not follow the optimal solution anymore. In fact, because of the existence of a stable local minima in the replica mutual information, it remains stuck in the non-specialized solution with high generalization error. Hence, it emphasizes a huge computational gap between what is theoretically achievable and what the conjectured best polynomial algorithm performs. To summarize, we provide a rigorous analysis of the generalization error, and we show that there exists a computational gap in the task of learning a teacher neural network. If you want to know more, you are welcome to attend our spotlight and poster presentation on the 6th of December.